much for coming tonight. Just a few little words before we start. We want to thank our principal sponsors, BP and Shell, for making this possible, and also Equinor, who are sponsoring our public programme, which you guys are part of today. We also have 10 more events, so you can check out our website. We've got QR codes on the wall if you want to take a look at that, but I won't blabber on too much, and I'll pass you over to you. Thank you so much for coming today, and we're looking forward to your talk.
Not at all. Thank you very much. Good evening, everybody. Thank you for taking the time to listen to our presentation here this evening. My name is Michael O'Sullivan. I'm the head of technology with RAB Microfluidics. So the presentation that I'm going to go through tonight is to talk about the technology, the company a little bit, the technology that's developed. And it's important to say about technology, it's the technology that was developed here in this university. So this is a company that had its origins in this university. So it's very nice to be back here to speak about that. We'll talk about why the company was set up, what problem it was set up to solve, and how we're going about solving it. Okay, so as I say, we'll talk a little bit about the journey that the company has been on, the problem we're solving, the challenges of the industry, what the current state of the art is, how we feel we are moving on and moving ahead of the state of the art and addressing an issue and solving a problem that the industry currently can't solve satisfactorily. We'll show our technology journey, look at the products that we have, how the genesis of them, how they developed to this point, and also what our plans are for the future. I should say as well that you will see a device here. This is our product, and you'll see a video of it online, but this is essentially our box of tricks. And I have it here because it will hopefully give you an appreciation of a device that is portable, which is going to be an alternative to a laboratory. So it'll hopefully give you some perspective. So the company. So we are a Scottish company, and more specifically, we are an Aberdeen-based company that was set up by Dr. Rotimi Alabi in 2016. The company was set up really for one purpose and one purpose only, and that was to diagnose early signs of failure in lubricated equipment using patented microfluidic technology. Talk a little bit about the microfluidics in a little bit. Dr. Alabi developed this technology following 4 years of research here at the University of Aberdeen. So it is very much a case of technology was born and has grown in this particular town, but more specifically in this particular university. At the moment, the team is of 10. We have a number of different disciplines. It's a multidisciplinary team involving physicists, chemists, mechanical engineers, electronic engineers, software engineers, and indeed data scientists. I'll explain a little bit about why data science a little bit later on. So the issue was, as identified, was to look at a problem, and it was a problem with heavy machinery. We're talking here about equipment, engines in large equipment such as ships, wind turbines, etc., that have faults. Any equipment that is lubricated, that has moving parts, inevitably is going to have a fault, a failure at some time in its life. And through extensive research during the formative part of the company, it was identified that the cost of breakdowns on equipment, whether it's cargo vessels, whether it's turbines, is very extensive. It was estimated back in 2020 that it was up to £5 billion worth of the cost of breakdowns and failures to business. Yet this was despite the fact that the industry was spending about £3 billion to prevent these things in the first instance. So clearly something wasn't working as it should do. So this was an industry problem, an acknowledged industry problem that the company set out to try and address. one of the things that became apparent because of the number and the frequency of failures was that the ability of the existing condition monitoring approaches to actually address the problem were limited. Technologies were not complementary, so there were a range of different condition monitoring approaches that were not necessarily compatible, would give conflicting results, were subject to interpretation, misinterpretation, depending on the competence of people who are actually doing the condition monitoring. Also, the processes tended to be quite manual and carried out infrequently. And as a result of being carried out infrequently, you would often miss things. So incipient faults that you might have will go undetected because of the relative infrequency with which you were actually doing the analysis. The most robust way of doing analysis of oil was commercial laboratories. But again, generally speaking, that was a laborious process to take the samples and get into the laboratories. It took time, and it took time to get the results. And generally, they're only carried out very infrequently. So while they're excellent, they're not necessarily excellent at monitoring an ongoing and developing fault. So in that context, we're looking here at, why oil condition monitoring? Why, of all of the different condition monitoring types available to us, what is the significance and what is the advantage of oil condition monitoring? What we're seeing here is that there are a number of different ways in which you can detect failure and ongoing failure. Oil analysis, vibration, thermography, noise, heat, and eventually you'll see a failure. But the advantage of oil is that it can detect a fault at the earliest stage. A lot of times when you start getting to the point where you can notice abnormal vibration or you can see elevated temperature, things have gone too far and it's very difficult to prevent the fault. Whereas in oil condition monitoring, you're capturing an anomaly at a very early stage where you might actually have the possibility of preventing the failure by interventions. So starting from that point of view and working on the assumption that oil condition monitoring is going to be the most effective way in which you can assess machine condition, the gold standard is a laboratory. And there's some pictures here of a typical laboratory. It's got a lot of different equipment. Each of those pieces of equipment have a specific function in mind. They will analyze for different components of the oil. So you've got to send in the first instance, you've got to send your sample to the laboratory. They will carry out a very, very comprehensive analysis. So when it comes to oil condition monitoring, that is the ideal. You will get, for example, you will get a very, very extensive list of analysis, chemical competition. So for example, you will get results on the composition of wear metals that might be in the oil, which will give you an indication of whether any of the metallic components are damaged, subject to wear. You will get information on contaminants. You will get properties of the oil, viscosity, acid number, base number. So you'll get a very, very extensive list of parameters of the oil condition at any given time. Typically in the industries that we're looking at, whether it's the shipping industry, whether it's the oil and gas industry, or whether it's the renewables industry, samples will be taken possibly once a quarter. In the case of the renewables industry, it'll be once a year. So you will get a very, very extensive assessment of the lubricant from the lab. But in a 1 year time, for example, you'll get 4 data points at most. Now that means that at any given time, you know the condition, but there is a long gap where you don't know what's going on. So if there is a fault developing, firstly you can't tell from just a single data point, and by the time you take the next sample in 3 months hence, you may have had failure in the equipment. So what we're looking to do is address some of those inherent weaknesses or deficiencies in the current state of the art. So what you have, in addition to the points I mentioned there, getting a sample to the laboratory, generates a very large carbon footprint. We're talking typically here about devices, equipment that are in hard-to-reach locations. It may be on cargo ferries that very, very infrequently come to port. They may be in offshore wind farms. So to get the sample to the laboratory is not a trivial exercise. It costs a lot. You're also subject to getting a lot of contamination and mix-up potentially, because you've got a sample taken in one area and it's analyzed in another area. So there's a lot of scope for mix-ups. And as I said before, it's not in real time, it's infrequent, and it's very, very manual. So these are the pain points that the current best practice has, and that's what we're looking to address. So our solution was to basically take the laboratory to the asset, as opposed to taking the sample to the laboratory. So we're using microfluidic lab-on-a-chip technology, which I'll touch on a little bit in a minute. The benefit of this, by taking a device, and it's this device here, which I'll talk a little bit, by bringing that to a site, it allows us to automate the process, make it semi-autonomous, allow people to make samples and analyze samples as frequently as they have, because they essentially have the laboratory on site. So the benefits of this is you get a continuous stream of data, so you've got more information. If there are faults developing, you have an opportunity to detect them. The prospects of getting a mix-up of samples are lesser, because essentially whoever is taking the sample is probably going to do the analysis at the same time, because the device, the technology is very easy to use. There's a low environmental footprint because you're not involved in transporting samples or people over large distances. And the cost is very, very low. So these are the benefits of this particular technology that we've developed. It's not a replacement for the laboratory, it is complementary to the laboratory. So for example, if you're using this technology, our microfluidic lab-on-a-chip technology, to assess the condition of oil, if we start seeing some trends developing, that may prompt the operator then to take a sample and send it to the laboratory for a more extensive analysis. So we see it as being very much complementary to the existing methodologies and providing additional information that supplements that. Just to touch a little bit on the microfluidics. So really we're talking about microfluidics, we're talking about manipulating fluids on a very small scale. The amount of fluids we're talking about are from microliters to milliliters, and the microfluidic chip that we're seeing here, through which the fluids flow, are again in the micrometer size. So what we see here is we've got a particular microfluidic chip, which, as you see, has got a number of channels in it. There are also what we call viewing ports here. This particular graph, or this particular picture, shows you what is happening. Because we're dealing with fluids in a micro scale, you have two co-flowing fluids that are flowing laminar, so don't mix. So you essentially have two fluids flowing, and you've got an interface here. In this particular, what we're seeing here is, here's a lubricating oil. So this is the oil whose condition you're concerned about and you want to understand. We have a solvent which is flowing in parallel with it. And what happens is that, as you can see here, contaminants, components of interest are extracted from the lubricating oil by the solvent, and we can then subsequently, using spectroscopy, examine what's in the extractant solvent. And typically, we're using optical spectroscopy then to analyze the fluids. So in essence, that's the technology, and that's what we use. And the chip itself is a very, very small chip. And because we're using microfluidics, we also use very, very small volumes of the fluids, whether it's the oil or whether it's the various solvents. And again, that is an advantage over the traditional methods. I showed you a little bit earlier a laboratory and what a laboratory analyzes for. Now, we're not analyzing the same for the same number of parameters, but we are analyzing for what are ones that allow us to determine a number of failure modes: contamination within the oil, and degradation of the oil, which in turn can point towards issues with the equipment itself. So we are looking at the insolubles content, so the amount of soot, for example, that's in the oil. We're looking at acid content and the alkaline reserve within the oil. We are measuring the viscosity. We are looking for the depletion of additives, which is an indication of the remnant life of the oil. And we're also looking at, fuel dilution. We can identify egress of fuel into the lubrication system. And through these, this gives us a very comprehensive and very early indicator of some failure modes of the equipment, not just the deterioration of the oil. So as a result of our approach, we're able to take very, very frequent streams of data. We can trend that data to allow people to see the historical behavior, but also look at the likely behavior of the lubricant if you do not intervene over the subsequent period. We don't have sample mix-up. The environmental footprint is low, and it's a very low-cost alternative or supplementary analysis technique to the existing methods. The journey. As I mentioned, the company was founded in 2016, so the development of our technology has taken quite some time, and prior to this, the technology was developed in the university. But the first manifestation of our device was a demonstrator in a laboratory here at the university. Subsequent to that, we developed some demonstrator equipment, much larger than what you see here on the bench, but these were demonstrating the technology, demonstrating the application of the technology for the target equipment that we were targeting. We developed a pilot device. This was a device which was a greater level of maturity, which again, we used in the field. Subsequent to that, we have then moved to what is the commercial device, which is now in the market. Below this, we're looking at other derivatives, other types of technology based on that will address the same problems, but in different ways. We're looking at a device, for example, that integrates directly with a piece of machinery so that you can put it in very remote locations where it isn't even possible to actually take samples. And these are just some pictures of proof of concepts. The reason for putting that there as well is to say that the company is a research and development company, so we're carrying out ongoing research and development into the application of the microfluidic technology to look at oil condition over a range of assets in a range of environments. I've also put some markers here into the future, because what we're also looking to do as a company is develop machine learning techniques, predictive analytics tools, so that with all of the data that a device captures, allow us to use machine learning, deep learning, to be able to make predictions as to the future behavior of the equipment, which is quite an exciting opportunity we feel for this technology. And eventually we want to get to a point where this particular technology doesn't require any user intervention whatsoever. We can put it in a hard to reach and hard to sense environments, such as, for example, in a nacelle of a wind turbine, in a fit and forget fashion, and continuously monitor the condition of a piece of equipment that otherwise you just cannot monitor at the moment at all. So the journey of the development of the microfluidic technology thus far has led us to this portable device, which you see sitting on the desk here, called Oleum Oracle. Oleum because it's a Latin word for oil, and Oracle because it provides information, provides insight. We also have a cloud analytics platform, and I'll show you a little bit later how this all works and sits together. So as I said, we're taking the laboratory to the site. So what we have here is we have the device initially deployed on a vessel, but it can be deployed on any particular asset. A measurement is made locally, and I'll show you the video as to how that's done in a moment. The measurement then is sent to a cloud, And then from the cloud, it's downloaded onto our analytics platform, which we call RAB Microfluidics. And using that, anybody with access can then look at the oil analysis results essentially when they are produced in the machine. So people on the asset locally will see them. They'll see them on the screen. But anybody remotely who's responsible, an asset manager, for example, will see those. They can see it for all of the equipment been analyzed by this device, and they can see the trends. And so therefore, they can make informed decisions about actions that they might want to take. So I'll just show a brief video of how the system works. I should say that an analysis typically takes about an hour to do, and that involves preparation.
The instrument uses a diluted sample and whole oil to directly analyze 4 components of viscosity, acid number, base number, and insoluble content in the oil sample. To prepare a diluted sample, mix 1 ml of whole oil sample with 3 ml of cyclohexane. Shake thoroughly and introduce into the sample reservoir and into the Oleum Oracle instrument. No preparation is required for a viscosity measurement. To make a viscosity measurement, simply introduce 0.3 ml of undiluted sample to the viscosity reservoir in the Oleum Oracle instrument. To analyze a sample, ensure the instrument is turned on and indicates system ready. This may take a minute from turn on. Once ready, on the touchscreen, select New Measurement, then select the engine from which the sample was taken. This information should already be pre-populated. The type of analysis to be performed between chemical analysis or viscosity. The instrument asks if you have the necessary pre-checks on the solvent and waste reservoirs, ensuring there are solvents in the solvent reservoirs and the waste reservoir is empty. Once confirmed, select Yes, input the engine running hours and click Submit. The instrument displays the percentage completion of a run and the process being undertaken at that percentage.
I should say that that's slightly accelerated. The process takes approximately an hour in real time, but the process of doing the analysis takes approximately 15 to 20 minutes. So there's a preparatory stage, then there is the analysis phase, and then there is a cleaning phase. All of that carried out automatically without any user intervention. From an application point of view, we've initially developed and trialed the technology for the marine vessel sector. We've identified that it's a sector where, particularly in this country, you've got an aging fleet that have a lot of issues with the engines. So the maritime sector is an obvious starting point. But in essentially any industry where you've got heavy equipment, and particularly heavy equipment with moving parts that require lubrication, is a potential application for this technology. Whether it's power generation, whether it's aerospace, the energy sector. Now, the energy sector is the traditional oil and gas sector, where you have gas turbines, you have generators on platforms, but also in the wind turbine sector, which is clearly a growing sector. And it also, again, has rotating equipment with gearboxes, transportation sector, and the manufacturing sector. So the exciting thing about our technology is that essentially any industry that has lubricated equipment, which is essentially every industry, is a potential target application for our technology. And that then poses the question of, how ambitious are we? Well, we want to enable predictive maintenance strategies through automated and data-driven solutions. But we want to do that essentially for all rotating equipment across a range of industries. And what we're really looking to here is we want to really improve reliability, availability of every valuable machinery in the world, and we'll do it one engine at a time. So our ambitions are quite large, but that's because the problem is very large and the opportunity is very large. Does anybody have any questions, comments, observations? Okay. If anybody wants to have a look at the device up closer, please feel free to come up. You can ask any questions and have a look around it. Thank you very much for your time.
Thank you. Thank you.
Sure.
Yeah.
So we have a question.
Yes.
Well, not really a question.
Okay.
Martha says this was great. Thank you very much.
You're very welcome. You're very welcome. It's nice to get good feedback from any source whatsoever.
I have some confused.
Yeah.
I know this viscosity is the very important protection of the fruit.
Yes.
How could you measure it?
How do we measure it?
Yeah, using the device.
So we have a technique where we're taking the fluid and we are pumping it through the system, and we're initially looking at the time it takes to get between two predefined points. And from that, then we can, using an algorithm, we can then determine the viscosity and the change in viscosity.
Yeah, but to my mind, I think about from the different scale, the fruits of the viscosity of the fruit is different. How could you offer the small scale, the result from the small scale to the large scale? You know, the fruit in the trainer, maybe he will surround by the different force. Maybe the main force is about the interchannel force and the vesicle force. These two forces to determine the viscosity of the fluid. So at a different scale, maybe the fluid, maybe the force on the fluid is different. So maybe I think at different scale, maybe the viscosity is different.
I don't think so. Alabi, do you want to answer a question there?
If you apply a certain set force to any fluid, regardless of the viscosity, and you monitor the time it takes to move from point A to point B, you can then trend how that viscosity, you can then determine the viscosity of the fluid by just monitoring the calibration. Yeah. So we have certain standards. So you have a range of viscosity standards from something like maybe 150 centistokes to something like 600 centistokes. And you have these standards that you can buy. And you apply a set force and just monitor the time it takes to move from point A to point B. And you discover that there is a very good trend, a very good correlation in terms of how they actually are spaced out. And that is what we then use to actually monitor the viscosity.
Oh, thank you.
Thank you, Larry.
Yeah. But that's a good question because it is a good question because the microfluidic aspect of the device is used to make chemical measurements. Viscosity is not a chemical measurement, it's a physical measurement. It's a physical quality measurement. And in as much as the scales we're using are very small scales, it is not done on the microchip.
Yeah. Thank you.
Any other questions or observations from anybody? Yes.
I want to ask for the
that all of you will have more knowledge about the effectiveness of the cyclohexane for extracting acids.
He definitely knows more about that than I do, that's for sure.
Right. So during my PhD, what we did, we tried different. So for extraction, you want to be able to extract normal alkanes, and even maybe beyond that. And what you discover is that there is a level at which you're able to pull out normal alkanes using different normal alkanes, if I'm to use that, if I'm to explain it that way. So you have pentane, hexane, you have cyclohexane, and to a different degree, they are able to extract certain things out of oil, and they extract it based on the solubility. Those extracted based on the solubility coefficients that they have. And what we have discovered is, or what we discovered during the PhD, Stephen was my PhD supervisor, by the way. And what we discovered was that hexane was was more efficient than pentane. So when we started working on this as a commercial product, we then said, okay, could we replicate this with cyclohexane because of the properties of cyclohexane? Now, the properties of cyclohexane were better than hexane in terms of safety. So on the safety aspect, cyclohexane was much better for us to use. And we discovered that it had almost similar solubility levels for us to extract all of the components of interest. And what we're looking at is extracting low molecular weight components from the oil, and that it's dependent on the diffusion coefficient. So we saw that it was still effective to do what we wanted it to do, and that's why we're using it. And it gives us safety benefits.
There's another aspect, and that's that the acids that make lubricating oil acidic are not very large. What's that?
Another good question.
So when Michael came in, he was opening it up. I tried to smell what solvent it was because it was cyclohexane. I couldn't smell it. You know, right?
We changed the solvent just because cyclohexane will give us better safety profile than hexane will.
Thank you very much.
Thank you.
Thank you for your attention and your interest.
Thank you all for coming, guys, and huge thank you to Michael.